Alright, this will probably set a world record in terms of the shortest mini lecture of the semester, so enjoy it while it lasts. This will just talk a little bit about how we look at molecular orbital diagrams for conjugated alkenes. And the prototypical example we'll use is a butadiene. But as we'll see, you can expand this to other conjugated alkenes as well. Okay, so, quick recap. A conjugated alkene basically means we're talking about every atom has a p orbital on it, or at least every atom in the pi system. So, that's a key. And then the other important thing to remember is that this is all about these multiple center molecular orbitals, and the reason why is because it explains things that we observe in the lab. So, for example, with butadiene, one thing that we observe is that when we try to rotate around that central C2-C3 single bond, something's kind of weird. There's kind of some resistance here. It doesn't really rotate so freely. It's difficult to get into this conformation, which is called the S-cis conformation, S standing for the single bond there. So that's kind of odd. It turns out that this is just basically a hindered rotation, which doesn't make any sense if that's a single bond. Furthermore, what's also kind of odd is that it's preferred for all 4 carbon atoms to lie in the same plane. And there's a nice illustration of that in your textbook. So those things are kind of hard to explain based on this picture. And another thing that's virtually impossible to explain is that this supposedly single carbon-carbon bond is ridiculously short for a carbon-carbon single bond. So what's up with that? It doesn't really make sense, and of course it explains the reactivity as well. We can't really explain that whole 1,2 versus 1,4 addition very well without looking at a multiple center molecular orbital. So let's do that. Remember that to build up these molecular orbital diagrams, the number of p atomic orbitals must be equal to the number of pi molecular orbitals and vice versa. So I'm starting out with 4 p orbitals. I must end up with 4 pi molecular orbitals. Let's do it. Start with the all bonding p orbital overlap. So all 4 p orbitals on these adjacent carbons are in phase. Alright, so no nodes means the whole thing is overlapping nicely, top and bottom. So we do have the nodal plane, but otherwise there's no nodes here. So what does that mean? Well, this is a very important molecular orbital because this one, pi 1, shows why there's a planar conformation preference. Absolutely, you don't want to rotate out of this plane and disrupt that overlap. It also explains the short C2-C3 bond length because we've got molecular orbital overlap here. All of those carbon-carbon bond lengths are the same. So this is kind of the most important molecular orbital in terms of explaining the properties we just went through in the previous slide. Alright, well, what next then? Well, no nodes here. We'll need 1 node here. Remember, it has to be symmetric as well. So if I have these 2 orbitals so that they can overlap, but there's a node here, it'll still be symmetric. Which is important. We have to have symmetry. But 1 node here, this makes this psi 2. I need 2 nodes here, and you can get 2 nodes with symmetry by having the center 2 p orbitals of the same phase, but opposite phase here and here. I really should have saved this mini lecture for St. Patrick's Day, I think, given all the green here. But anyhow, again, illustration that we've got some molecular orbital overlap in between C2 and C3 here, but as we'll see, this is an empty molecular orbital, so that doesn't contribute to the shortened bond length. And then finally, as we would easily predict, the highest energy molecular orbital for butadiene is all antibonding. So there's no overlap between any of these p orbitals. So this was pi 3, pi 4, and now we have the 4 molecular orbitals, multi-center molecular orbitals for butadiene. We have 4 pi electrons in the pi system. So we fill them lowest energy, next lowest energy. So this is what our molecular orbital diagram looks like for butadiene. This is the occupied molecular orbital that is highest in energy, our HOMO, psi 2. And this is the unoccupied molecular orbital that is lowest in energy, our LUMO. So, the fact that both pi 1 and pi 2 are filled helps to illustrate the properties that we were talking about. That we have some reactivity of the isolated pi molecular orbitals in pi 2, but more importantly, this fully delocalized molecular orbital pi 1 illustrates the shortened CC bond length and the hindered rotation. So, it's illustrative to compare the molecular orbital diagrams of these conjugated systems to those of an isolated system like ethylene. So if you consider this kind of midline energy level between the bonding molecular orbitals and the antibonding, where for ethylene, of course, it's very simple. We only have 2 molecular orbitals, bonding and antibonding. Once you start working with conjugated systems, you kind of squish in the molecular orbital energy levels into the same kind of energy space, energy window. In other words, as we come up with more and more of these multiple center molecular orbitals, the energy level between the molecular orbitals gets smaller and smaller. So you'll remember in UV, we talked about promotion of an electron from a pi molecular orbital into a pi star molecular orbital, which I need to get that phase in there. So this energy transition took a lot more energy for an isolated alkene like ethene than it does for a conjugated diene, which is exactly what we saw in UV. So promotion from pi to pi star, no big deal, a very small energy gap, and as we get more and more conjugated, say a hexatriene, for example, that gap gets smaller and smaller. This is not a very good drawing, of course. So that is the story of the molecular orbital diagram for butadiene. And the question would be, can you expand this by doing the same sort of exercise for a conjugated triene or tetraene, etc.? So I'll leave you to that while I go get something to drink before I choke here. So, world record, only 10 minutes. Yay, I'm figuring this out. See you later.